4.8 Antiderivatives. The outline of this video is as follows. We will begin by exploring the core idea of an antiderivative, which is essentially the reverse process of finding a derivative. I will show you how, if you know a function's rate of change, you can work backward to find the original function itself. Then, we will establish a systematic method for finding what we call the general antiderivative, which accounts for an entire family of possible functions. After we have the mechanics down, we will apply this concept to a very practical area, motion problems in physics, where we can determine an object's position from its velocity. Finally, I will introduce the specific mathematical language and notation we use for this process, known as the indefinite integral. Our goal is to master the tools for reversing differentiation and see how they are applied. Let us explore how to work backward from a known derivative to find the original function, a process that is essential for solving many real-world problems. This reverse process is called antidifferentiation. Formally, we can define an antiderivative this way. A function, which we can call capital F, is an antiderivative of a function, which we can call lowercase f, if the derivative of capital F of x equals lowercase f of x for all x in an interval. For a tangible example, think about motion. If you know the acceleration of a falling object, you can use antidifferentiation to find its velocity. Then, you can apply the process again to the velocity to find the object's position at any moment in time. In short, finding an antiderivative means answering the question, what function has this given function as its derivative? Now I will explain that a function has an entire family of antiderivatives, not just a single one, and they are all related by a simple constant. For example, we know an antiderivative of 2x is x squared. However, the function x squared plus 1 also has a derivative of 2x, because the derivative of any constant is 0. This insight leads to a crucial theorem. If f of x is any one antiderivative of a function, then the most general antiderivative is f of x plus c, where c is an arbitrary constant. This constant c is often called the constant of integration. Geometrically, this family of functions represents a set of curves that are just vertical shifts of one another, like the parabola y equals x squared being moved up or down. The essential point to remember is to always add this constant c to represent all possible antiderivatives. Let us practice finding antiderivatives by essentially reversing the process of differentiation we already know. The core task is to look at a function, like f of x equals 2x, and ask ourselves, what function, when I take its derivative, gives me this result? From our experience with the power rule, we know that the derivative of x squared is exactly 2x, so x squared is an antiderivative. We can apply the same backward thinking to trigonometric functions. Since the derivative of sine of x is cosine of x, an antiderivative for cosine of x is sine of x. This even works for more complex functions, like 1 over x plus 2 times e to the power of 2x, whose antiderivative is the natural log of the absolute value of x plus e to the power of 2x. The essential takeaway is that you can always confirm your answer by differentiating it to see if you get the original function back. Now that we know an antiderivative represents a whole family of functions, let us see how to select just one specific curve from that family. We can pinpoint a particular antiderivative by using an initial condition, which is simply a requirement that the function must pass through a specific point. The task of finding an antiderivative that satisfies such a condition is called an initial value problem. For example, let us find the antiderivative of 3x squared that must equal -1 when x is 1. First, we know the general solution is x cubed plus some constant c. To find that constant, we apply the initial condition, we set 1 cubed plus c equal to -1. Solving this simple equation shows us that c must be -2. This gives us the particular solution we were looking for, which is the function x cubed minus 2. An initial condition removes the ambiguity of the constant c and gives us one unique function. Let us visualize what the general antiderivative, y equals x cubed plus c, actually represents. This equation describes not a single function, but an entire family of curves, where each curve is a vertical shift of the basic shape y equals x cubed. The constant of integration, c, determines the specific vertical position of each curve on the graph. For example, a c value of 2 shifts the curve up by 2 units. An initial condition, like requiring our function to pass through the point 1, -1, acts as a selector. It forces us to pick the one specific curve from this infinite family that satisfies our requirement. As the figure shows, only the curve where c equals -2 actually passes through that point. The key takeaway is that an initial condition turns a general family of solutions into the one particular solution we need. Now that we know what an antiderivative is, we can build a toolbox of formulas to find them, and you will see that these are just our familiar derivative rules in reverse. The most fundamental is the power rule. To find an antiderivative for x to the power of n, we first increase the exponent by 1 to get n plus 1, and then we divide by that new exponent. For instance, an antiderivative of x squared is x cubed divided by 3. This rule works for any power n, with the single exception that n cannot be -1. The same reverse logic applies to our trigonometric functions. Because we know the derivative of cosine of kx involves sine of kx, it follows that an antiderivative of sine of kx is -1 over k times cosine of kx. This pattern of reversing a known derivative rule is how we find all the other antiderivatives listed here. The key is to see the function as the answer to a differentiation problem you already know. Let us continue building our list of essential antiderivatives, focusing now on exponential functions and forms that lead to inverse trigonometric functions. For the natural exponential, the antiderivative of e to the power kx is simply 1 over k times e to the power kx. The rule for a general base, like a to the power kx, is very similar, but we must also divide by the natural log of the base a. The one case the power rule could not handle was for the function 1 over x. Its antiderivative is the natural logarithm of the absolute value of x. Finally, we have 3 formulas that come from the derivatives of inverse trigonometric functions. You should learn to recognize these specific patterns. An integrand with a square root of 1 minus a squared term suggests an inverse sign, while a fraction with 1 plus a squared term in the denominator points to an inverse tangent. Recognizing these specific algebraic structures is the key to applying the correct antiderivative formula. Let us put our new formulas into practice by finding the antiderivatives for a few common functions. For x to the power of 5, I will use the power rule. We add 1 to the exponent to get 6, and then divide by that new exponent, giving us x to the power of 6 over 6 plus c. For 1 over the square root of x, the crucial first step is to rewrite it as a power, which is x to the power of -1/2. Applying the power rule again, adding 1 to the exponent gives +1/2, and dividing by 1/2 results in 2 times the square root of x plus c. For the function sine of 2x, the antiderivative is negative cosine of 2x, but remember we must also divide by the inner constant, 2. Likewise, for e to the power of -3x, the antiderivative is itself divided by the constant in the exponent, which is -3. The key is to match the function to the right rule and carefully account for any constants. Now that we have a table of basic antiderivatives, we can see how to combine them to handle more complicated functions using what are called linearity rules. The first is the constant multiple rule, which says that the antiderivative of a constant k times a function f of x is simply k times the antiderivative of f of x. The second is the sum or difference rule, which allows us to find the antiderivative of a function like f of x plus or minus g of x by finding their individual antiderivatives first and then adding or subtracting them. For example, the antiderivative of 5 times x squared is just 5 times the antiderivative of x squared, which gives us 5 times the quantity x cubed over 3. When you combine functions this way, you only need to add a single constant of integration, c, at the very end. The essential point is that these rules let us find antiderivatives term by term, just as we did with derivatives. We can now combine our basic antiderivative formulas to solve more complex problems using linearity rules. These rules simply state that we can find the antiderivative of a function piece by piece, handling sums and constant multiples separately. For our example, the function is 3 times the square root of x plus the sine of 2x. First, using the constant multiple rule, we take the known antiderivative for the square root of x, which is 2 times the square root of x, and multiply it by the constant 3 to get 6 times the square root of x. Next, using the sum rule, we simply add the antiderivative we already found for the sine of 2x, which is negative 1/2 times the cosine of 2x. The final result is 6 times the square root of x minus 1/2 times the cosine of 2x plus c. The main takeaway is that you only need to add a single constant of integration at the very end of the process. I can now show you how finding an antiderivative is the same thing as solving a simple but important type of equation. This is called a differential equation, which is just an equation that involves the derivative of an unknown function, y. For an equation like the derivative of y with respect to x equals f of x, our goal is to find the original function y. The first step is to find the general antiderivative, f of x plus c, which we call the general solution. This represents an entire family of functions. To narrow it down to one specific function, we use what is called an initial condition, which is a single point that our solution must pass through. For example, we might require that y must equal 10 when x is 2. Using this known point allows us to find the exact value for the constant c, giving us a particular solution. So, an initial condition turns an infinite family of possible solutions into one unique answer. Let us see how antiderivatives provide a powerful tool for describing motion, allowing us to work backward from acceleration to find an object's path. We already know that velocity is the derivative of position, and acceleration is the derivative of velocity. Antidifferentiation simply reverses this. If we know an object's acceleration, its velocity function is one of the acceleration's antiderivatives. Likewise, the position function is an antiderivative of the velocity function. For example, if we know a ball's constant acceleration due to gravity, we can integrate to find its velocity. But we need an initial condition, like its launch speed, to find the specific constant of integration. To find the one correct path, we must know these starting values. In short, by using antidifferentiation twice and applying initial conditions, we can fully determine an object's motion. Now we can apply our understanding of antiderivatives to model the motion of a dropped object, which is a classic physics problem. Our goal is to find the height of a package over time after it is dropped from a rising hot air balloon. We start by modeling its velocity, which we can call v of t. Since the only force is gravity, the acceleration is a constant negative 32 feet per second squared, giving us the differential equation d versus dt equals negative 32. The package initially shares the balloon's upward velocity, so our first initial condition is v of 0 equals 12 feet per second. Next, we model the height, s of t. The rate of change of height, ds dt, is simply the velocity. The package was dropped from 80 feet, giving our second initial condition, s of 0 equals 80. To find the final height equation, we must solve these two initial value problems one after the other. I will now use antiderivatives to solve a classic physics problem, modeling the motion of a package dropped from a rising hot air balloon. First, let us establish our initial conditions. The balloon is moving upward at 12 feet per second when the package is released. So the package's initial velocity, written as v of 0, is positive 12. It is important to remember that the package inherits the balloon's motion. Its velocity does not start at 0. The package is dropped from a height of 80 feet, so its initial position, s of 0, is 80. Once dropped, the main force I will consider is gravity, which causes a constant downward acceleration. Since acceleration is the rate of change of velocity, we can write this as the differential equation dv over dt equals negative 32 feet per second squared. The value is negative because gravity pulls the package downward in the direction of decreasing height. These three facts give us the complete mathematical model we need to find the package's position at any time. Now that we have a model for acceleration, our first step is to find the package's velocity at any given time by solving an initial value problem. This type of problem combines a differential equation, here dv dt equals negative 32, with a specific starting point known as an initial condition. First, we find the general antiderivative of the acceleration, which gives the velocity function v of t equals negative 32 times t, plus an unknown constant of integration, c. To find the specific value for c, we use our initial condition that the velocity at time 0 was 12 feet per second. Plugging these values into our equation, we see that c must be equal to 12. Remember, without the initial condition, we would have an entire family of possible velocity functions. The specific velocity of the package at any time t is therefore v of t equals negative 32 times t plus 12. Now that we have the velocity, we can find the package's exact position at any time by solving a second initial value problem. The rate of change of position, ds dt, is our velocity function, negative 32t plus 12. To find the position function, s of t, we take the antiderivative of velocity, which gives us negative 16t squared plus 12t plus a new constant of integration, c. To find this specific constant, we use our initial condition for position. The package was dropped from a height of 80 feet, so s of 0 equals 80. Plugging in t equals 0 makes the first two terms disappear, which shows that our constant c is simply 80. Therefore, the particular solution that gives the package's height at any time t is s of t equals negative 16 t squared plus 12t plus 80. Now we can answer the final question. How long does it take for the package to hit the ground? This occurs when its height, s of t, is exactly 0. We start by setting our height function equal to 0, which gives the equation negative 16t squared plus 12t plus 80 equals 0. This is a quadratic equation, which we can solve for the time set by using the quadratic formula. Applying the formula gives us two possible solutions for time. One is a negative value, and the other is a positive value of about 2.64. Since time in this physical problem cannot be negative, we can confidently discard the negative root. The only physically meaningful answer is that the package hits the ground about 2.64 seconds after being dropped. Now that we know an antiderivative represents an entire family of functions, we need a formal way to write this collection, which is called the indefinite integral. We use a special symbol, an elongated s, called an integral sign. The function we are integrating, f of x, is called the integrand, and the dx at the end specifies that x is our variable of integration. This notation directly connects to our previous work. If the derivative of a function capital F is the integrand, then the integral equals that function capital F plus our arbitrary constant c. For example, we can now write that the integral of 2x dx equals x squared plus c, which neatly packages the entire family of solutions we found earlier. In short, the indefinite integral is our standard notation for the most general antiderivative of a function. Now let us see how our linearity rules make finding complex antiderivatives much simpler. Our goal is to evaluate the indefinite integral of the quantity x squared minus 2x plus 5. Because we can integrate term by term, we can break this problem into 3 smaller pieces. Finding the antiderivative of x squared, then of negative 2x, and finally of 5. Using the power rule, we find these are x cubed over 3, negative x squared, and 5x, respectively. Technically, each of these parts produces its own constant of integration. But we can combine them all into a single arbitrary constant, which we simply call c. This is a crucial simplification you will always use. So, the final general antiderivative is x cubed over 3 minus x squared plus 5x plus c. The main idea is to integrate each term separately, and then add a single constant c at the end. Let us summarize the essential ideas of antidifferentiation we have covered. The core concept is finding a function, which we can call capital F, whose derivative is our original function, little f. Because the derivative of any constant is 0, the most general antiderivative is a whole family of functions written as capital F of x plus c, where c is an arbitrary constant. To find a specific function from this family, we need an initial value problem, which provides a single point that our function must pass through. This condition let us determine a specific value for the constant c, giving us a particular solution. We use a special notation for the general antiderivative, the indefinite integral of f of x dx. This entire process is incredibly powerful, as it allows us to work backward from a rate of change. For example, to find an object's position by starting with its acceleration. Let us wrap up by applying what we have learned to see how these concepts work together. The first question here reinforces a core idea. Any two antiderivatives for the same function will always differ by a constant, because the derivative of any constant is 0. We can use this principle to solve a classic initial value problem, like the second question about a particle's motion. First, we find the general antiderivative of the velocity function, which is 3t squared minus 4, to get the general position function, t cubed minus 4t plus c. Then, we use the initial condition that the position at time 0 is 5. Plugging this value into our general solution shows us that the constant c must equal 5. This allows us to find the unique position function for this specific particle. The key takeaway is that an initial condition let us pinpoint the one particular solution we need from an infinite family of possibilities.